Good afternoon, everybody, and welcome to the CPS seminar today. As we have been doing for this term, we have another of our own members of staff giving us a talk on their recent work. In this case, it's a great pleasure to introduce Benjamin Béri from the Theory of Condensed Matter group. Benjamin did his PhD in Hungary at the Eötvös-Loránd University, which is, of course, a very famous name in physics. He afterwards was at Leiden and in TCM before becoming a faculty member at Birmingham, and we were lucky enough to attract him back to Cambridge, where he is now prospering once again in TCM, and indeed we are prospering thanks to his presence. He does a huge amount of different areas in his work, which I won't attempt to list, but all over condensed matter physics. And today he'll be talking about hidden structures in a model of many-body quantum chaos, and I look forward to understanding the title by the end of the talk. So at the end, we will switch to a different link where there's an interactive chat room for questions, because we found before that that's more effective than using the text boxes for chat. So I'll remind you at the end, but everyone should bear in mind that you have to switch links to go to the chat session if you'd like to discuss further with Benjamin at the end of the talk. So thank you, Leona. If you could switch over to Benjamin now.
So thank you. Thank you for the kind invitation, and indeed thanks for organizers, especially Leona, for setting all this up. So in this talk, I will describe a recent work on a paradigmatic model of many-body quantum chaos. But before I would start, I would like to highlight my main collaborator in this. He's Jan Berends. He is an excellent postdoc with me in TCM, and he did and really still does in our ongoing work on the subject much of the heavy lifting in all this. Okay, so the model that I'll talk about is the Sachdev-Kitaev or the SYK model. I'll focus on its variant where the basic objects are Majorana fermions, and I'll define these more properly later on, but for now I'll just denote them by these blobs. So the SYK model involves a collection of Majorana fermions. I'll denote their number by K. In this figure, which aims to symbolize this collection, I think K is equal to 16, and I hope I counted them correctly. This model has all-to-all interactions, and as we'll see, it's only interactions. I will describe it more mathematically a bit later on. But for now, I would like to just mention what elevates this SYK model to a level of a paradigm. And these are these two words with quotation marks, that it is a solvable model of maximal quantum chaos. Maximal here is understood in a sense of a suitable quantum many-body variant of the butterfly effect, that is the sensitivity of the outcome, this delta xt, on the initial conditions, this delta x node. This sensitivity is characterized by Lyapunov exponent lambda L, which in this SYK model, when it is at temperature, has this form 2 pi kBt over h bar. And this result is to be compared to a famous one by Maldacena, Schenker, and Stamford, who on quite general grounds argued that in complex quantum systems, the Lyapunov exponent, so that this butterfly effect, actually has an upper bound. It is smaller than this 2 pi kBt over h bar. So the SYK model saturates this bound. The quantum chaos in this model is in this sense maximal. And this feature is actually shared by some seemingly unrelated systems, most notably certain black holes. These also have this maximal Lyapunov exponent. And so this and some other similarities to black holes raise the question that has been a motivation of immense level of activities with this SYK model, namely, is the SYK model a toy model of the holographic duality, which is a duality between quantum gravity and some quantum field theory, or in this case, more of a quantum mechanics model. But at the same time, there is also an immense level of activities surrounding Majorana fermions in the solid state, both from theory and in experiments. In this context, Majorana fermions are some exotic emergent particles, or I should actually be more precise the way I call them. They should be really called Majorana zero modes. But knowing myself, I'll just call them Majorana fermions. And for now, I'll just denote them still by these blobs. So in this solid state, these Majorana fermions are some spatially localized objects in certain superconducting devices. The theoretical ideas for this go back again to Kitaev, the Kitaev in the Sajdavia-Kitaev model. So he was the one who highlighted the principle in this 2001 paper that I list there. And then came Fu and Kane, and a bit later Sau, Luchin, and Oreg, who suggested some concrete paths towards realizations. In all these paths, the main idea is to use a clever combination of some spin orbit coupled materials, which are available, some forms of superconductivity, which is again available, and magnetic fields. So here I show these three pictures. They are from the experiments. On the left is the micrograph of the first, of the device in the first Majorana experiment. That's from the Kaunhoven lab in Delft. This was in 2012. Then in the middle, that's not a micrograph. That's a sketch of a system from a recent experiment from the Yazdani lab at Princeton. And then on the right, it's again a micrograph from a very recent experiment from the Marcus lab in Copenhagen. So these leftmost and rightmost figures focus on the same paradigm. This paradigm was put forth by Sau, Luchin, and Oreg papers. Here the idea is to use a spin orbit coupled nanowire adjacent to an ordinary and S-wave superconductor, and to apply a magnetic field along the wire. The Majorana fermions are predicted to appear where the superconductor terminates, so I try to indicate that with the blob and this arrow. And these experiments are designed to test the presence of this Majorana there with conductance measurements. The sketch in the middle that focuses on this bit earlier idea by Fu and Kane, or at least on a related idea. Here the spin orbit coupling comes from a so-called topological insulator that is again adjacent to a superconductor, but the magnetic field comes now from ferromagnetism. And these Majorana fermions in the solid state have several fascinating features. Here I would like to highlight just two, I think, important points. Firstly, as I alluded to it earlier, these Majorana fermions are particles that emerge from the collective behavior of a many electron system. And they actually give a really profound illustration of the concept of emergence. So even though underlying constituents, the electrons, are fermions, these Majorana fermions are not. In fact, they are neither bosons nor fermions. And to see what they are, it's useful to consider, again, a many electron quantum state with at least 4 Majoranas. I'll denote it with this oversized cat with 4 blobs in it. So one can consider interchanging, say, Majorana 1 and 2. This turns out to implement a unitary operation, U21, on this state. But we can also consider interchanging Majorana 2 and 3. This again implements a unitary operation. I denote this now by this U32. So far, you may just think that's just all heavy notation for something that's familiar, because fermions and bosons, they do the same thing. You exchange 2 of them and you get a unitary operation. It's simply a multiplication by +1 or -1. You get the +1 for bosons because the wave function is symmetric under particle exchange, and the -1 for fermions because of the antisymmetry. But for Majoranas, the situation is much more interesting. There, the 2 operations, this U32 and U21, they don't commute, so the order in which we do the exchanges matter. When we have some non-commuting operations, then we have something that we call non-abelian. So because of this, we say that these Majoranas obey non-abelian statistics. And what's more, it turns out that these operations UAB are very robust. They are quite insensitive to the precise details of how we execute them. So this suggests that these can be used as quote-unquote fault-tolerant quantum gates. So Majorana systems may serve as some building blocks for quantum computations. One can use Majoranas to build a quantum computer. So that's, I think, really a tantalizing idea. Take these Majoranas and achieve fault tolerance at the hardware level. But one wonders, is this really a tantalizing enough idea for somebody to put serious money behind it and to compete against paradigms such as superconducting qubits backed by Google? And actually, it turns out that it is tantalizing enough, yes. So as you see these headlines, Microsoft has spent a lot of money on this. Indeed, it has now a worldwide network of labs, including the Kauenhoven lab in Delft with this first Majorana experiment, and Marcus lab in Copenhagen with the rightmost figure. And they are really making wonderful experimental progress. So here we have these two interesting things. Firstly, the SYK model with its potential black hole holographic dual, and their exotic Majorana fermions in the solid state. So given these two concurrent ideas of interest, one might wonder, could we use these Majoranas in the solid state to build black holes, or at least their duals, in our labs? And what I highlight here are indeed some theoretical works proposing this. One is even called black hole on a chip. The two ideas that are highlighted differ in the concrete path to realization that they consider. The topmost one works with this topological insulator-based idea, while the bottom one is with these spin-orbit nanowires. As a condensed matter theorist, I shall also take solid-state Majoranas as my SYK motivation. But I will focus on structural features, so I will remain more or less agnostic about the device implementation. So in other words, I'll just take the SYK model as a starting point. I'll take it as a given without worrying too much about the specifics or challenges of these proposed realizations. This being said, there are of course a few observations that will guide my research questions. So the first ones are about the SYK model. As I mentioned, it is a solvable model of maximal quantum chaos. But there are, of course, some caveats. Firstly, both the solvable and these maximal attributes require that K be much larger than 1. Recall K here is the number of Majoranas. And secondly, this suitable many-body variant of the butterfly effect in reality amounts to a so-called out-of-time ordered correlator. So to measure this, and therefore measure the Lyapunov exponent, what we need to do is to take an initial state, then hit it with this Majorana at time 0, then hit it with another Majorana at time t, then hit it again with the Majorana at time 0, then hit it again with the Majorana at time t, and see how the outcome compares to the initial state. So this process needs time to evolve, at least effectively, forward and backwards, which is already something that looks quite challenging. And to make things worse, this quantity, this out-of-time ordered correlator, often suffers from quite strong finite K effects, meaning that this K much larger than 1 requirement is understood quite strictly. If I compare to the situation with Majorana devices, there the number K of Majoranas currently is order unity. And at least I think the hope is that in the medium term is to have devices with maybe a bit more than 10 Majoranas. That's surely not much larger than 1. And secondly, we should also consider measurements that are most natural in the solid state. They do not really evolve time back and forth. For example, the tunnel conductance is instead closely related to this 2 Majorana objects which come in time order. This leads to the questions that I would like to discuss. Firstly, can we have some interesting features of SYK physics for moderate values of K with a moderate number of Majoranas? And secondly, can these be features that have signatures accessible in the standard kinds of measurements? So in the rest of the talk, I would like to discuss this, and I'll try and follow this plan here. So first, to make things more concrete, I would like to first introduce the SYK model and Majorana fermions, but this time beyond blobs. And then once we have those ingredients, then I would like to unfold the structure of symmetry and some emergent objects in this SYK model. We'll see that there appear some robust structural features that are present in all regimes of K, and which influence the behavior already for a moderate number of Majoranas. And then in the last part of the talk, I'd like to describe some signatures of these features and the kinds of observables related to solid-state experiments. So then I'll start with introducing SYK and Majoranas beyond blobs. So now these blobs become these gamma S. These are Majorana operators or Majorana fermions. I'll tell in a minute what they are. And the SYK model then, as I said, it's a model with K Majorana fermions, but now I also show the Hamiltonian. So here, the only thing is that the coupling constants are real. This is required by hermiticity, but there is no other structure. They are structureless, or you can take them random. And as you see, all possible 4 Majorana terms are featured. So in this sense, it's an all-to-all interacting model. But I come back to that from a more physical perspective in a moment. But so now what are these Majorana fermions or Majorana operators? They are simply Hermitian operators that square to the identity and they mutually anticommute. So in the language of high energy physics, these are just some higher dimensional gamma matrices. There is, of course, another viewpoint, the one prevalent in condensed matter. Majorana fermions are Hermitian and anti-Hermitian, or if I'm a bit colloquial, real and imaginary parts of a fermion. So you see in this formula, from a pair of Majorana fermions, you get a conventional fermion satisfying this usual anti-commutation relation. And maybe it's useful to know that it really doesn't matter how one pairs up the Majoranas into fermions. If you look at this this collection of Majoranas up in the corner, I intentionally included a quite awkward pairing to emphasize this. No matter how you pair them up, you always get a valid set of fermion operators. Now for a second, just let's go back to the experimental systems from this perspective. So what my previous point means about these Majoranas being real and imaginary parts of fermions is that we actually have superconducting devices that decompose electrons into real and imaginary parts. I think this is pretty fascinating. So this figure is another micrograph. It's from a very recent paper from the Kouwenhoven lab in Delft, where they really tested something like this. What they studied is whether if a Majorana on the one end appears, then we have a Majorana on the other end. That is, if you take our collection of electrons, which are fermions with both real and imaginary parts, then if we end up with a real part on one end of the device, then do we end up with the imaginary part in the place on the other end where we expect it. But now going back to a more mathematical perspective, this 2 Majorana equals 1 fermion correspondence has important implications for the Hilbert space on which this SYK model acts. So for K even, we can pair up the Majoranas in whatever way we wish. So we have a standard fermion Hilbert space. But for K odd, to get a fermion Hilbert space, we have to include an extra Majorana, quote unquote, at infinity. Physically, this can be some Majorana or Majoranas even in terms of this nanowire system at the ends that we are not interested in. So with this preparation, I can now also make it more concrete what I mean by the SYK model being interaction only. If it did have a non-interacting part, that would be quadratic in these Majorana operators. It would feature a so-called Bogolyubov-Desjardins Hamiltonian, this HBDG, as a coefficient matrix. And to see why this is non-interacting, what one can notice is that if one diagonalizes this Bogolyubov-Desjardins Hamiltonian, then this expression transforms into contributions of independent occupations, so degrees of freedom that are manifestly non-interacting. In the SYK model, we don't have such a quadratic term, which is why the SYK model is interaction only. In fact, the SYK terms instead generalize density-density type interactions. And to see this, what one has to know that the density itself is a valid non-interacting term. So for example, non-interacting electrons couple through their density to the electric scalar potential. So because of this, the density must be this quadratic object on the right. But then density-density interactions translate into these quartic objects, just like the terms in the SYK model. So now we have all the ingredients to discuss the symmetries and these emerging objects in the SYK model. Starting with symmetries, it's good to start with unitary symmetries. These by and large amount to conserved quantities. So I just mentioned density-density interactions. So the first thing one might try is particle number, which is this sum of this fermion C dagger C expressions. But this actually won't work. We have all the possible 4 Majorana terms in the Hamiltonian, which means that we also have all the possible 4 fermion terms in terms of C and C dagger, including the terms like the one on the right there. And this adds 3 fermions and removes 1, so that doesn't conserve the number of fermions. But even such terms can't switch between an even and an odd number of fermions. In other words, they can't change the fermion parity. The Hamiltonian therefore commutes with the fermion parity, and therefore as a matrix, it is block diagonal with 2 uncoupled parity blocks, this H plus and H minus. So first, let me just condense all this up here in these 2 lines. As it turns out, actually fermion parity, or almost, we'll see slight modification in a moment. This is all there is about unitary symmetries. The next thing to look at are anti-unitary symmetries. So these are symmetries of the form T equals U times K, where U is a unitary operator or unitary matrix, and K is the operation of complex conjugation. And this actually is not as artificial as it might seem. Take, for example, time reversal in single particle quantum mechanics. So just thinking intuitively, time reversal applied at some moment in time keeps the coordinate x invariant, but it reverses motion, hence it flips the momentum p. Quantum mechanically, this means that the position operator x is invariant under this t, but the momentum must change sign. But then in this derivative, that inherits the invariance from the coordinate x. So for this sign reversal to take place, the imaginary unit must change its sign under t. So this t must involve complex conjugation. And indeed, studying complex quantum systems according to their anti-unitary symmetries has a very long history. It dates back to the origins of random matrix theory. This little highlight that I have here is from a classic paper by Freeman Dyson. You see I highlighted that he uses time reversal invariance, that is an anti-unitary symmetry, to achieve a classification. And maybe it's an interesting side note. I was quite impressed to see that already in this 1961 paper, the title refers to complex systems. In my mind, I thought it's at least 30 years more modern, this expression complex systems, than this. So I'm quite impressed with this. There is another paper about anti-unitary symmetries and classifications that I would like to highlight before moving on. This is by Alex Artland and Martin Zirnbauer. This paper is by now also a classic. They used anti-unitary symmetries to classify complex, in this case chaotic or disordered, but essentially non-interacting fermion systems. By adding the ingredient of superconductivity, they found new symmetry classes. By now these are called Artland-Zirnbauer classes, and that's how I'm going to refer to them. And these have features that are different from those studied by Dyson in that paper and Wigner beforehand. And here there is another little side note. So if you look at the title of this Artland-Zirnbauer paper, it refers to normal superconducting hybrid structures. So this may remind you of these Majorana micrographs that I showed. Those are also normal superconducting hybrid structures. And this is actually not at all a coincidence. These things are really all interrelated. But now let me return to the SYK model and first recall this block diagonal form in parity grading. And so now one can ask about the anti-unitary, or as we just saw, time reversal-like symmetries of each of the parity blocks. These anti-unitary or time reversal-like symmetries, they can be absent, then I denote it in this little table by Hans-Lachey, or they can square to +1 or to -1. And it is a key finding by this paper that I highlight by Yu, Ludwig, and Zhu, that these three possibilities as a function of k, which again is the number of Majorana fermions, displays this eightfold pattern that I show in this table. And in fact, these three possibilities translate precisely to the three ensembles introduced by Dyson. You see I highlight three such ensembles are studied in detail. And these ensembles govern the level spacing statistics. The period 8 pattern of this level statistics, which I indicate below in these graphs for the SYK model, they toggle through this Wigner-Dyson threefold way as one changes k, the number of Majoranas, is another key result from the same paper by Yu, Ludwig, and Zhu. But then one may still wonder, looking at symmetries within just a parity block, is this really the end of the story? It really is sufficient only if one focuses on observables through which these different parity blocks don't talk to each other. But before I will discuss more on this, I would like to tell a little bit about what actually prompted me to wonder whether there may be something more to this eightfold story. At that stage, I didn't know much about the SYK model, let alone thought about parity in it, but I saw this table with this eightfold pattern of these three possibilities, and that reminded me of something I was familiar with. It looked like a row in some table that I saw somewhere else. And in fact, that was this Artland-Zirnbauer paper, this Artland-Zirnbauer classification of non-interacting fermions. In fact, what it classifies is this Bogoliubov-de Gennes Hamiltonian. So just recall, as I show it in this bottom line, this HBDG, this Bogoliubov-de Gennes Hamiltonian, is this coefficient matrix for a non-interacting theory. So when classifying these possible forms of this HBDG, we have two types of anti-unitary symmetries. It's T plus that commutes with HBDG and T minus that anti-commutes with it. And so the row that we had before, see I try to nicely overlay it, that we can associate with T plus because due to the commutation with the Hamiltonian, this will be responsible for the level spacing statistics. So the kind of distributions that I showed just a bit earlier. Then we can add the corresponding allocation as per this Artland-Zirnbauer classification for T minus, and then we get to this by now well-known table of 8 so-called real Artland-Zirnbauer classes. So real here means that the system must have at least one of these T plus or T minus. There are also complex classes. These are those without anti-unitary symmetries. Of these 8 classes, I should highlight, 2 are already included in Dyson's earlier classification. These are this A1 and A2. These are the ones which have T plus only. The other 6 classes are new to Artland and Zirnbauer, Or more precisely, they introduced 4 of them as properly new classes. These are the D, D3, C, and C1. These are so-called Cartan labels, but that is not important for us, really. So these label superconducting systems. And then there are the remaining 2 in this table, BD1 and C2. These were known from random matrix theories of quantum chromodynamics. But it was really Atlan and Zirnbauer who realized that they all belong to one larger classification related to another branch of mathematics where this labelings A1, BD1, and so on also come from. But so that's a nice story, but might it just be all an interesting coincidence? After all, this classification by Atlan and Zirnbauer is a classification of non-interacting systems, and the symmetries there really depend on the forms of the couplings in the Hamiltonian. In contrast with the SYK model, we work with an interaction-only system, and we work with a fixed form of coupling. And what toggles the pattern is K, the number of Majoranas. So the next question is then, how does this K-dependent Atlan-Zirnbauer structure emerge for this interaction-only model? So this is what I would like to try and explain next. And for this, I'll combine ideas from 2 papers. One is this U. Ludwig Zhu work that I mentioned with the period 8 Wigner-Dyson pattern. And the other is a work of Fitkovsky and again Kitaev on classifying one-dimensional interacting fermion topological phases. And to do this, I'd like to almost start over and be a little bit more systematic with the SYK symmetries. So let's start again with the unitary symmetries. We have already seen that fermion parity is a symmetry, and when K, so the number of Majoranas, is even, that's all the unitary symmetries that we have. When K is odd, then we have actually another unitary symmetry. I denote it here by this Z. This is a product of all the Majorana operators involved in the Hamiltonian. So this commutes with all of the local Majorana operators. By local, I refer to the operators in the Hamiltonian, but it anti-commutes with the Majorana at infinity. We introduced this Majorana at infinity just to have a fermion Hilbert space, if you recall. And so these features, this commutation and anti-commutation features, actually make this Z quite useful later on, because it can be used to diagnose whether some complicated operator is local, so involves just this K Majoranas 1 to K, or it involves the Majorana at infinity. And just another little note that we could have actually just as well used as a unitary symmetry, the gamma infinity. It beautifully commutes with the Hamiltonian as well. But that is not an independent symmetry from the others. It turns out to be this parity P times this Z. So let us now look at the anti-unitary symmetries. I find it useful to establish from scratch here that these anti-unitary symmetries for this model may square only to plus minus 1. So for this, the first thing to note that for T to be an anti-unitary symmetry, it has to commute with all this gamma Q with a Q independent sign. That's because of the structureless nature of the couplings. Actually, the commutate or this transformation can be with a plus minus, as I said, but with Q independent signs. But then we can take the sign simply to be plus without loss of generality, because the complementary choice is supplied by P times T. So the next thing is that T squared is unitary. T was anti-unitary, but if you square it, it's unitary, and it commutes with all the Majorana operators. That means that this T square actually can be just a phase. Here I'm invoking Schur's lemma, which I'm not going to try to prove here. But the other point that I want to highlight, and which I'll prove in that line at the bottom, is that in addition, T is anti-unitary, as we just saw, and this means that this T square is plus minus 1. And that is really easy to prove. So in this bottom line, we say that T cube equals T cube. I just broke it up into T square T. I think that's quite uncontroversial. But then if we plug in this phase factor for a T square, we see that T and this phase factor must commute with each other. But remember, T includes complex conjugation, which means that this phase factor must be invariant under complex conjugation. So that means that it can be just plus or minus 1. So from here, let us now try to get some t plus minus and some k dependence. To see how this goes, I'll focus on the case when k is even. Okay, that's again the number of Majoranas. So this t plus minus and one aspect of this k dependence both come from considering the interplay of this t with the parity. For this, it's useful to rewrite this parity first in terms of our conventional fermions, C, and then if one writes that out, one finds that parity is simply the product of all the Majorana fermions times the imaginary unit on the power k on the 1/2. But then, noting that T is such that it commutes with the Majorana fermions, but at the same time it is anti-unitary, how it interplays with the parity really comes down to whether this prefactor I on the k/2 is real or imaginary. So this allows us to introduce a t plus when t leaves parity invariant and t minus when it flips the parity. And these happen for different values of k. We have t plus when k is twice an even number, t minus when k is twice an odd number. And here I introduce t plus the way I did because, again, I would like it to be a symmetry of a parity block so that it will govern the level spacing statistics. Now, another aspect of k dependence comes from working out what the value of t square is. And this t square is actually basis independent because recall that t square is plus minus the identity, and plus minus the identity is plus minus the identity in whatever basis we are. So we are free to choose a convenient basis, and this will be one where the Majoranas as matrices are such that those with odd labels are imaginary and those with even labels are real. Then, taking our T and decomposing it as a unitary times a complex conjugation, the invariance of these Majoranas under T leads to a relation between the unitary and the Majoranas. And then we can solve for these relations. Again, they have different solutions depending on whether k is twice an even or twice an odd number. When k is twice an even number, then we can introduce a parity just for the odd labeled Majoranas, and that happens to do the job. When k is an odd number, then we can introduce a z for the even labeled Majoranas, and that will again work. And then we can work out the squares of the corresponding operators, which happen to be t plus and t minus based on our parity considerations above. And putting everything together, we arrive to these cases highlighted with red in the table. So we find the results for A1, classes A1, D, A2, and C. And so note in particular the two cases here with k mod 8 equals 2 and 6. These are interesting because neither of them has a t plus squared, so they have the same level statistics in the sense of Dyson, but they are distinguished as class D and class C because of their t minus square in the sense of Atland and Zirnbauer. So we went beyond just a threefold Wigner-Dyson pattern repeating in a eightfold structure. We now have Atland-Zirnbauer classes. So with this, we have described the structure of symmetry, and this is valid for any regime of K. Next, let me describe how this leads to certain emergent objects. Specifically, what we'll see that the SYK model supports so-called exact many-body zero modes. These are some fermion parity odd objects that commute with the Hamiltonian. But I'd like to highlight already now that these zero modes are really unlike usual conserved quantities, for example, angular momentum, because those are bosonic. They are fermion parity even. The objects we are looking for here are fermion parity odd. So instead, what these things are really are some new examples of so-called strong zero modes, a concept introduced by Paul Fendley. He's a big professor in Oxford for certain many-body analogues of Majorana fermions. And the presence of such objects, these zero modes, should actually be a bit surprising since the SYK model has completely structureless couplings. But as we'll see with the symmetry structures that we just established, they really arise naturally and unavoidably. So many-body zero modes can be viewed as special cases of eigenoperators. These are operators whose commutator with the Hamiltonian is just a number times themselves, and the zero mode arises when this number is zero and the operator is fermion parity odd. In the free fermion case, these eigenoperators are simply the fermion operators diagonalizing the Hamiltonian. In the interacting case, there is some earlier work on this. This is an approach that was based on converting this eigenoperator equation on the left into a standard eigenvalue problem. But this has some drawbacks, namely, if the original problem was m by m, then the eigenvalue problem inflates up to m squared by m squared. But it also has some advantages that the locality of the operators obtained this way, that is the exclusion of this gamma infinity, is automatic. This work with this approach focused on problems that included quadratic terms, but another drawback was that they could establish the existence of zero modes, but they could count how many there are only for weak interactions. Here I'd like to offer a much more direct approach, and the spirit of it is something that we are familiar from undergraduate quantum mechanics or linear algebra. Namely, if you can diagonalize your Hamiltonian, you know everything about that Hamiltonian. And with that in mind, here's the recipe for getting all the eigenoperators. You can get them simply in terms of the eigenfunctions and this eigenoperator eigenvalue in terms of the eigenvalues. So in this way, we get m squared eigenoperators. We get a complete system without blowing up the problem to n squared times m squared. And the degeneracy of this eigenoperator eigenvalues directly follows from the level degeneracy in the original Hamiltonian. So we can count the zero modes in particular for any interactions. And of course, we can directly apply this to the SYK model. It's very general, but the locality for an odd number of Majoranas needs some further care, but it's all doable in general and in a concrete way. So when applying this to the SYK model, there are two things to consider. The first is parity. Since parity is a good quantum number, eigenoperators will have two types, and we care about the odd parity ones. These are built out of eigenvectors with opposite parity. The second aspect is locality, as I just mentioned. This is not an issue when k is even, because then we don't have Majorana at infinity, but for k odd, one has to pay attention, and this is where this operator z comes in, that tests the locality. One has to ensure that our eigenoperators commute with z. And these operators that I show here actually do the job. So with all this, we can now see when we have many-body zero modes in the SYK model. Putting together these parity considerations with the general expression with the zero modes, we see that we have many-body zero modes whenever there is a parity degeneracy in the spectrum. And the zero mode operators with the formula even in the even k case have this form. I'll focus on this even k case from now on for concreteness. So here I just summarize what we learned about zero modes so far, in particular that they are guaranteed to exist when we have parity degeneracy. But then we should tell when is it that we have parity degeneracy. This is when we have a T minus. This is because T minus commutes with A, but it anti-commutes with the parity. Therefore, if we have an eigenstate psi, then T minus psi is also an eigenstate with the same energy, but with the opposite parity. Furthermore, when parity is the only degeneracy, which is the case in the cases that I'll focus on, then this opposite parity eigenstate, psi minus p, can simply be taken by applying T minus to psi p, the other eigenstate with the opposite parity. So in terms of this table, we can then see that many-body zero modes are there in 6 out of these 8 classes. In fact, they are there in all the non-Dyson classes. And I'll be focusing on this class C and D that I circled with yellow. Firstly, in these classes, taking them as examples, as I said, we can immediately count the zero modes. Applying this general formula in the squared box on the top, we find that we have as many of them as the Hilbert space dimension, k on the k half, 2 on the k half. Second, I already highlighted these classes because they are interesting in that they have the same level statistics, but now because they have different t minus square, the zero modes might behave differently and have different consequences in correlation functions. So let me quickly, I see I'm a bit maybe running over, but let me a little bit illustrate this. So we have already seen that this Atlan-Zinnbauer class dictates the presence or absence of zero modes, and I would like now to discuss how that impacts the amplitude of the zero modes in individual Majorana operators and what the observable consequences of this is. So again, here I just repeat what we know about the zero modes. I'll still focus on k even. The zero mode classes are the C and D in this case. And so, as I said, let's look at the single particle amplitude, that is the contribution of a zero mode to a Majorana fermion. So the point to remember is that the eigenoperators give a complete basis in operator space. So we can expand a Majorana fermions in terms of these eigenoperators, and we would like to know the zero mode contribution in this expansion. From this general expression for the zero mode that is squared there, it follows that the coefficients, this u for the zero mode contribution, are given simply by this matrix element, which in turn, due to the relation between opposite parity but equal energy eigenstates, are equal to this diagonal expression. And then comes another insight, is that this thing in this diagonal expression, this matrix, is again anti-unitary. So we can again worry about the square of this. And what turns out is that what it squares to is the same as t minus square. So this square will be different in class C and class D. And there is a general property related to these squares, namely when this t minus square equals to -1, then this corresponding diagonal matrix element is guaranteed to be 0. Some of you may be familiar with this because of Cramer's degeneracy. This is the same logic. But when it squares to 1, then it is generally non-zero. So there is some difference between class C and D because of how the t minus square behaves. And this is again reminiscent actually of a free fermion scenario, namely there's a similar pattern for the presence and absence of single particle zero modes. But here we are talking about a single particle contribution, in the SYK case that is, of many-body zero modes. So I'll just conclude by discussing the observable consequences of all this, and I'll focus on the spectral function at infinite temperature and still on the case when the K, the number of Majoranas, is even. I highlighted this in red in this table. So just to remind, this A1 and A2 are the Dyson classes, C and D are Atlan-Zinnbauer classes. And the reason I focus on infinite temperature is because I would like to emphasize that these zero modes and the features that they lead to, they are not ground state properties. The features are similar to what would be found at any temperature, including at the ground state, but also for some correlation function with respect to some eigenstate high up in the spectrum, so some violently non-equilibrium quantity. And so the spectral function, actually it has some complicated expression, but these are the key features. It decomposes into a zero mode contribution A0 times the delta function, and this non-zero mode contribution A tilde. The zero mode term is absent in these Dyson classes A1, A2, since these classes have no T minus, there is no parity degeneracy, so no parity zero modes. But furthermore, even this A tilde, this non-zero mode contribution, is also different between this Dyson and Atlan-Zinnbauer classes. For Dyson classes at small omega, low energies, there are no features, but it decays as omega square in this class CD, in the Atlan-Zinnbauer classes. That's because in the latter case, we have cross-parity level repulsion because of the cross-parity degeneracy. In the former case, the two parity sectors are independent. And furthermore, this zero mode term, this single particle amplitude, again, is now different between class C and class D in the two superconducting classes. It is 0 in class C because we don't have a single particle amplitude, but it's non-zero in class D. So one can summarize all this in this little box in the bottom. So at low energies, the Dyson classes are featureless. Class C has a spectral hole because it's omega squared decay, and class C has a spectral peak. And so here's how it looks in terms of the numerics. Here we see the infinite temperature spectral function for various system sizes for all the 8 symmetry classes, and we do some ensemble averaging. And if you look at it, you see the featureless small omega behavior. You really have to go to small omega, so ignore these waves in these classes A1 and A2 in the Dyson classes. And you see the spectral hole for class C and also C1, and the spectral peak for class D. I should say that this spectral function is a quantity that is related to scanning tunneling spectroscopy in the solid state. And so that concludes my talk, really. If I may just summarize, we have uncovered 2 interrelated kinds of hidden structures. The first kind of structure was that the SYK model has Altland-Seinbauer classes, not just Wigner-Dyson classes. And these not only give rise to this periodate pattern of features, but also lead to another kind of structure, many-body zero modes. And these zero modes, in turn, have signatures in correlation functions. I focus on the single particle spectral function, whereas we just saw they give rise to spectral holes and spectral peaks, but they also have consequences in the time domain, including also in the so-called out-of-time order correlator, this many-body variant measuring the butterfly effect. If one continues thinking about these structures in zero modes further, it turns out they lead to further features such as many-body myelinoformians and even quantum mechanical supersymmetry. I just advertise it here. The details are discussed in the PRL we published with Jan this year. And this really concludes. So let me just emphasize that all these structural features that emerge, they are present for any regime of K. The signatures are present already for a moderate number of microRNAs. So while we may not be building black holes in the lab anytime soon, there are interesting things to explore about the SYK model that are closer to medium-term microRNA devices. Thank you for your attention, and sorry if I overrun a little bit.
So thank you very much. That was fascinating.
Thank you.
Who has done a little bit of work in high energy physics and indeed on weird black holes. It's amazing to see the completely different perspective that you bring to the topic.
Thank you.
If we were in real life, of course, there would be wild applause from all over the auditorium, but we can't do that at this speed. But I hope that many people will be waiting to join on the other link, which we shift to now, so that people can ask questions. And I think I will not try and moderate those. I will let people ask the questions as they come. But I suggest everybody moves over to the other session for the interactive part. So thank you very much again. And
thank you.
The audience, remember we're having CPS seminars. It's an opportunity for us all to get together as a department. And I hope to see at least see your number count online next week. Thank you very much.
Thank you.